Good afternoon, everybody who's joined. Thanks for tuning in after we had a little bit of a break. So this is going to be the first talk of a three-part series that's going to stretch past the holiday next week. And this week, it's going to be an introduction to the National Research Platform. And then in 2 weeks, it'll be talking about a use case on NRP, ESNet, and Sense. And then the week after that, it'll be inter-testbed networking with FPGAs across Fabric using NRP. So it'll be a couple talks in a row that are all a little bit interrelated. This one is meant to just give everybody a little bit of a base knowledge to understand what's going on with NRP. And we have two speakers today, Mohammad and Elham. And Mohammad is going to be sharing the slides, but both are going to be talking. And I think, Mohammad, you said you're going to be starting us off.
Hi all, thank you all very much for joining us today. My name is Mohammad Sada, and joining me is my colleague Elham Khoda from both of us from UCSD and the San Diego Supercomputer Center. And Elham is gonna be introducing the National Research Platform.
Right. So if you go to the next slide, at the beginning of the talk, we are going to tell you about the National Research Platform, like why it was created, the main motivation, and what our larger goals are. So to start with the challenges, this project it's a long-standing project. So this project was started by recognizing the challenges, which are listed at in the bullet points of the first 3 points here. So there's a rising demand of cyber infrastructure for research and education. And you can see largely there is an inequality between the institutes that has this kind of resources and the institutes that don't have this kind of resources. So this access inequality is a big issue, particularly the smaller institutions and community colleges. They're struggling as large scale computing is becoming a mainstream in different research and different research domains and education. And also there is this architectural evolution that happened post Moore's law, because as the Moore's law is slowing down, you would see a lot of different varieties of architecture available in the market, and that also actually complicates the domain science adoption because it's kind of difficult to adopt with a new kind of architecture as things are moving very fast. So to address some of these challenges, the National Research Platform, came into play, and then we as we go through the talk, you'll see like we try to address many of these challenges. Some of our future goals, of course, I mean, although we are trying to address these challenges, we are not there yet. Some of our future goals are prioritize the CI access for all institutes, and then also just make it a universal connectivity, connecting all the educational institutes, the small colleges and medium colleges, all across the US. Largely, we are now working with a lot of community colleges in California, then essentially creating a platform for global collaboration and innovation. So the next slide, please. So the National Research Platform, it's a partnership between almost 70 institutions. There are three main institutions, the UC San Diego, the University of Nebraska-Lincoln, and then the Massachusetts Greenfield HPC Center. These are the three main institutions which are in the main grant, the current main grant. But then there are lots of institutions which have been, partners throughout the journey of the National Research Platform. Um, the fundings are mostly coming from the National Science Foundation, and there are fundings are also coming through the Department of Energy, Department of Defense, and few other sources. So the NRP operates primarily a Kubernetes distributed cluster, and this cluster is largely in the US, but it's actually we also have some nodes outside the US, so it's technically is operational in three continents, and so Asia, Europe, and North America, and the cluster is called Nautilus, and we'll go through some of the details of the cluster. So the platform itself, largely in the US, as I mentioned, the three centers you can see the UCSD, the middle there's a Nebraska Lincoln, and then on the East Coast there's a MGHPCC. And there are distributed data infrastructure, like Internet 2 provides us local caching and also all other sort of infrastructure. And although these are the three main centers, there are lots of institutions who are all connected to the same platform. So if we go to the next slide, I'll tell you a little bit about the whole distribution. So this is the dashboard. You can actually find this dashboard on our website. It's dash.nrpnautilus.io. It's connected to our main website as well, and you can see how the institutions are distributed all across the US. We're kind of zooming in to the US only, but there are places in Europe like CERN and also in Asia and Korea and other places. And this list is actually growing every day. So we have that's why we have this dashboard where we can kind of see the current status. At the moment, you can see there's 82 sites, 412 nodes, and over 1,400 GPUs there. And yeah, and then I'll go to a little bit of more details of the Nautilus in the next slide, where I'll talk about how the cluster is running. So the cluster has been running for over 6 years. There's various storage options like CBMFS, the CephFS, the S3. There are advanced monitoring tools like Sonar, there are Traceroute, Prometheus. There are diverse computing and data tools like JupyterHub, ODM, GitHub, GitLab, Nextcloud, Overlive. There are collaboration and communication tools like Jitsi, Etherpad, Hedgetalk, and SyncThing. There are over 425 nodes, as you just saw in the dashboard. There are over 1,400 GPUs, lots of FPGAs, over 50 FPGAs. There's two Bluefield SmartNICs, and then there are some smart SSDs and programmable Tafino suites. And it continues to the next slide with more details of the hardware. We have over 400 connected 6 NIC cards. There are a bunch of P4 programmable Tafino switches. We have 32 programmable Xilinx Alveo E55C FPGAs, 16 B2R FPGAs, 3 Xilinx Alveo SM1000 FPGAs, 7 NVIDIA Bluefield 2 DPUs, and 2 Xilinx U2 FPGA Power Smart SSDs. And then, so this is a Kubernetes cluster, and all of them are, kind of included in the cluster, and most of them are accessible to the users. Some of them are you need special permission, but then pretty much everything is accessible to the users. If we go to the next slide. So this slide shows you like number of GPUs and a little bit of details of the CPUs. So we already kind of talked like we have lots of CPUs and GPUs, over 1,400 GPUs. The type of GPUs actually vary in a wide range. We largely have NVIDIA GPUs. Almost all our GPUs are NVIDIA. We have high-end GPUs like NVIDIA A100, 80 gig. There are 144 of them, which are very good for machine learning model training and other sort of intensive AI work. And then we also have kind of low-end gaming GPUs like RTX and GTX, although like some of them might retire soon. But those are still good for doing regular low, like less intense GPU work. And then we also now have 8 Qualcomm Cloud AI 100 Ultra inference cards. So these cards are inference cards. So at the moment you can't really do any machine learning model training there, although they have the capability of doing fine tuning. But largely at the moment we have been using them as inference cards, and these are also available to public users in general. One card is 4 SoCs, a system on chip, and then it's essentially we have like 4 times 8, like 32 the units, and you can request any number of SoCs in your job. And these are very fast, and these are very fast. Just wanted to highlight that these are very fast, and each SoC is actually capable of running like 25 billion parameter LLM. So it's kind of very powerful card. So if we go to the next slide, moving on to the storage options, we already kind of highlighted the 2 slides back that we have various types of storage options. So we have Ceph file system, the CephFS. We have Ceph Redis block device, Ceph RBD, We have lean store blocks, we have ST compatible storage, and we have also Open Science Data Federation or SDF. So all of these type of storages are, and we have lots of description about these storages in our doc, and we often do our regular consultation with for the users, like bi-weekly meetings to kind of help users to choose which type of storage is good for their workflow. But largely for shared, if there's a large group and you want to share data and files between the members of the group, the SFFS is probably the way to go. But otherwise, if you are doing something on your own and there is no necessity of sharing the data and files with others, then the block devices like link store block and the safe RBD blocks are pretty good and quite fast as well. And we also have S3 and OSDF, which are usually good for large amount of larger data, like a read and write. OSDF mostly for reading, and S3 is usually good for read write both. But yeah, like I said, our doc kind of describes quite a bit of use cases, and we always there to help users to choose which option is good for them. So if you go to the next slide. So we will now talk about some of the services that we run on our cluster. There are several services, as we pointed out at the beginning. Many of them are collaborative services like Overleaf and other things. But then the main two services which are largely used, one of them is the JupyterHub service. So NRP has two JupyterHubs running. Largely the JupyterHub West, that's the most popular one. And many users, they use it. Many university instructors, they also use the JupyterHub West for their classrooms or giving their students for practicing their assignments and other things, other homework. But we also have instructions to run your own hub. So I'll talk about that in a second. But these hubs are all, it's very easy to use. You can see in the screenshot right inside, there are these server options. You just choose which region you want to run GPUs and CPUs and how much RAM you want to use. There is also, of course, some limitations like how many GPUs you can use and how much RAM you can use through this JupyterHub interface. But it's largely very good for doing most of the work. And NRP also provides several pre-built images, and many of them are suitable for most of the data science workflows and machine learning workflows, as you can see on the right-hand side. And we have our doc, which kind of describes you how to use it and many other use cases. And I was telling that in case you are not happy with the images that are provided here and you want some more privilege on for your group or for your work, so there is a way to run your own JupyterHub, and then those kind of instructions are also given in our doc. If you go to the link, you'll be able to see it. So if you go to the next slide, so these JupyterHubs are largely used for classrooms. This gives you an interactive access. It's very easy for users like students who are not particularly user of the Kubernetes cluster. They can use the JupyterHub using their institutional credentials. We have over 1,000 users, which is all across 47 institutions. And we also have namespaces using the JupyterHub. So we have over 100 namespaces deployed their own JupyterHub, like I just mentioned. And one of the things that we are also started doing since last year is that we have started supporting the near classroom, which is the NSF initiative of offering resources for classroom education. So instructors can essentially use our platform for their classroom, and we kind of provide them some support. And they largely this near classroom supports are through JupyterHub. And I'll talk a little bit in the next slide. But next slide, please. So at the moment we have over 10 allocations, and they largely we support them to kind of launch and deploy their own JupyterHub, and then they can use it whichever way you want. And there are some advanced use cases, and there are so they try to integrate a lot of other services on top of JupyterHub. And there are some examples you might see here and there on our doc and other places. So if you go to the next slide, the other service which is quite popular and in general largely used is called Khoda. And this is one of the main one of the services which gives you access to the FPGAs in very easy way. I mean, you can of course use the FPGAs through your namespace by writing your own Kubernetes config file and everything. But that could be a little bit tedious, and sometimes you have to do a little bit of juggling around to get all the configurations correct and actually be able to access the resources. But then we have this easy way of accessing through Coder. The Coder templates are basically images plus config, and we have lots of pre-built templates. So Mohammad is basically takes care of this Coder, and you might have heard him talking about Coder in different other platforms. There are a bunch of different templates. We have U55C FPGA virus workflow image, which has an ESNet FPGA SmartNICs workflow, and these images come with many of these images. Many of these templates come with pre-built Xilinx runtime tool installed, and on top of that, several other things like Xilinx tools and everything is kind of configured. And there are also certain images which are good for using regular data science and Python workflow, like for certain machine learning work and other things. And you have the ability to request the hardware. The config, it's also like very easy to use. Like it has similar kind of starting window like JupyterHub. So you request your sources and everything, and you start your workspace. So that's basically your personal workflow. So one thing is that we still don't have the ability to share your workflow or workspace with another collaborators as of now. If you are working in Coder environment, it's on your own, so you can't share it with someone else. Like the same thing is true for Jupyter at the moment as well. And link to our doc talks about a lot of different things and use cases. And if we go to the next slide, to continue with the Coder, we have custom Kubernetes workflows with Terraform, and that's one of the features of the Coder. It essentially launches pods and deployments, and it comes with a lot of different options. You can run remote desktop through the coder with no VNC. There's a screenshot here you can see at the bottom and central bottom. You can run VS Code on your browser. You can run VS Code locally. So you have two different ways of running VS Code. It's kind of very easy and handy to code and use it. You also get a terminal in browser, so that's also like the middle picture. And there's a persistent personal SSH key ability, and there are also like lots of Coder apps that you can actually experiment and try using them. It's like a bunch of agents and AI apps nowadays available. Mohammad can tell probably more if you have any questions later. But yeah, so Coder and JupyterHub, those are the two very popular ones and largely used and very easy to use with a lot of support and pre-built functionalities there. And if you go to the next slide, that's so apart from these two services, there are lots of LLM. Those are also hosted. So we've started running our own, the free public LLMs are hosted on the Nautilus resources, and you can access them through this. If you go to this llm.nrp-nautilus.io, you can see all the LLMs that are hosted, and all these LLM like NRP managed LLMs are also like described in our doc. And there are a few different apps. If you go to the next slide, there are a few different apps which are there, like so the LibreChat and anything LLM. These are like two different interfaces through which you can actually interact with the models that you saw in the previous slide. You can actually choose which model you want to interact, and there are like opportunities of collaborating, creating groups, and all sort of things, and yeah, so so this is like for chatting, and in fact you can also like use there are API calls that you can make, so you can basically use our NRP managed LLMs seamlessly within your code without paying anything. So if you go to the next slide, that's my last slide. I'll pass to Mohammad after this. Well, so far we have talked about the NRP project, largely the goals and the motivations. We have talked about the Nautilus cluster, a little bit details about what sort of services running, what's the hardware, and then largely focused on two different services like JupyterHub and Khoda. Now, the most important thing is that if you have any issues and running into trouble or having difficulties um, accessing the cluster or others, all any sort of issues, like this is the place to go. Where support is mostly by this metrics channel. So this link, if you click nrp.ai contact, that sort of gives you the link to the metrics. You can download the metrics on your desktop. You can also use the web app as well. And then the Nautilus support channel, that's the main channel where most of the admins are active. And if you ask any questions, you'll see someone will answer you within a few minutes. Apart from that, there is an NRP news channel, which is super important to kind of follow and subscribe to that, because that channel is that's our main way of announcing any sort of service, any sort of maintenance work is going not working, or any new feature coming up. So that's the main place to go. So with that, I'll just pass it to Mohammed, and he'll continue the rest of the presentation. Thanks.
Great. Thank you very much, Elham. So just to continue the conversation, as we provide resources in multiple campuses, multiple institutes, we attempt at providing a cloud for academics in general, and that introduces some pain points. And why would network operators care about those pain points? Is just to illustrate the kind of environment, the kind of ecosystem that we're dealing with, is that by comparison to hyperscalers, I know we relatively have humble resources in terms of hyperscalers being an academic cluster. But that makes us run into some very interesting challenges in being heterogeneous and spread both horizontally in supporting multiple sites, multiple institutes, and vertically in supporting multiple software environments, different kinds of hardware, and a very wide variety. So as you saw, as Elham has explained, we have a large number of types of and models of GPU cards, as well as FPGAs and SmartNICs and switches, network devices, and novel compute architectures such as the Qualcomm Cloud AI 100 Ultra inference cards. And that introduces some pain points, mainly with dealing with lots of firmwares, drivers. One example is that, for example, Intel or slash Altera FPGAs, in some cases, some of them are not supported by Intel and Altera for Kubernetes support, where they have a device plugin. That's one pain point where we have to provide an environment where experimenters, researchers can provision these cards within of Kubernetes. Another example is that for example, FPGAs and SmartNICs that do network workloads use applications like DPDK normally require huge pages, IOMMU grouping, and that makes it a necessity for them for the host to host the card, and the card's not reliant on, for example, composable hardware such as PCI composing racks and such and so on and so forth. Along with that, a lot of hardware uses custom kernels. A lot of them don't play nice with Kubernetes, and sometimes the custom kernels conflict in supporting two hardware types on the same hardware node, and that's where we have to do some engineering to figure out either patching the kernels ourselves or conflicting dependencies and finding solutions for those, or so on and so forth. And of course, in that model, we support virtual machines over Kubernetes with KubeVirt on almost every node on the cluster, where users can also provision KVM virtual machines along Kubernetes. As Elham mentioned, we have JupyterHub and Coder for easy access for novice users who are not familiar with Kubernetes, which is an ideal environment for classrooms. But we also provide Kubernetes native solutions as access points. For example, you can deploy the Slurm Helm chart to support Slurm within Kubernetes, combine other clusters with Admiralty, and there's plenty of other access points, different access models where we try to support everything. And in trying to support everything, also there's a very wide range of hardware. We have ARM nodes, we have x86, 64. In that hardware, we also have different link speeds and bandwidths. We have 100 gig nodes, we have 25 gig nodes, which makes it a challenge also in network experiments, which is what we're trying to focus on in this part of the talk. And provisioning bandwidth to users, which is something that we heavily rely on ESNet Sense on, which I'll talk a little bit more in the next slides. But in what we provision a dual stack Kubernetes cluster that is running IPv4 and IPv6. With Calico, Multus is also available as a CNI in Kubernetes. As Elham mentioned, we have relatively more than 400 ConnectX 6 NIC ports that are available. So each one of our nodes, or the standard configuration, is that there's a ConnectX 6 NIC or something similar. And more often than not, is that one NIC port is used for deployment. That is the NIC that is connecting the node to the rest of the cluster, to the public internet, to the network, so on and so forth. But the other port in a lot of cases is available for provisioning through Kubernetes with Multus. That makes it available for network research, for establishing topologies and network experiments on Nautilus, which is what I'm gonna dive a little bit into here. Is that how is that done on Kubernetes? Is that we rely on Sense, and the ASNet Sense has an orchestrator that dynamically configures VLAN IDs and VLAN ranges for establishing L2 paths. So what that means is that users on NRP can use Sense to start an L2 path over a VLAN tag that starts an interface on the physical node. And users can use Multus then to attach that that interface that started from the physical node onto their Kubernetes pod. And that allows them to have a Docker container that has the network interface connected, and then they can have, for example, two endpoints on the cluster that have quality of service, that have a direct L2 connection over a dedicated interface that they have autonomy over. They can establish topologies over and so on. And it's interesting here to mention that many of NRP's nodes are part of the Audible Sense topology. As you can see here on the map, so this is on this slide, the top left corner, this is ESNet's network and ESNet sites. And on the right side is Internet 2. And both ESNet and Internet 2 have provided network backbone for NRP and many of the NRP sites. To have the screenshot you see on the bottom right that Elham previously showed of multiple NRP sites, and here we're limiting it to the United States for the sake of simplicity for all four maps. And this allows us interconnectivity and interoperability and combining experiments, which is where it gets very interesting for researchers, is where you have multiple ecosystems, with NRP being one of them, and you can combine your research work. Such an example would be the Fabric testbed, which you can see here on the bottom left corner. These are also the Fabric sites in the United States also. You can see here by comparing the map on the right and left is that there are multiple campuses, multiple sites where both NRP and the Nautilus cluster and Fabric coexist. And that gives us plenty of room for, let me call them creative experiments that rely on ESNet Sense. This is where I'm going to dive a little bit into what ESNet Sense is. So Sense is short for Software Defined Network for End-to-End Network Science at Exascale. It was developed by ESNet Sense, and mainly, without getting too deep into what it does, is that it allows users from their end to start end-to-end provision paths, L2 and L3 paths across the infrastructure, so users don't have to deal with what's under the hood. They request quality of service, intent-based API requests, and they have their paths. And the way it works is that for NRP, for example, nodes that are provisioned by ESNet Sense have something called a resource manager that has real-time tracking of the network infrastructure and resources that are available and bandwidth available. That's what it provides to the API. There's also a very easy to use Python library where users can provision paths in scripted ways. And that allows connection to very interesting places, including Internet 2 and ESNet endpoints. as well as other ecosystems, not just the Fabric testbed. Starlight and Caltech are two, Chameleon Cloud, other federated testbeds, and so on. And this is also an interesting point to mention something about our talk that is happening in 2 weeks on July 11th. So on that talk, we're going to be talking about more deeply about ESNet Sense and how it works on NRP and how to start quality of service L2 paths on NRP with experiments that involve pods. Uh, our aim here is to provide an introduction to NRP with this talk so users are familiar with what we provide, what our goals and outlooks are, and the variety of resources that we have. In 2 weeks, we will have an interactive, let me call it demonstration or talk, where we can provide you with hands-on examples in running network experiments on the National Research Platform. And between now and then, there's 2 weeks where so everybody on this call is more than welcome to start using the cluster, experiment, and go through our docs, experience the cluster, see what we have to provide. So whoever's attending in the talk in 2 weeks, you'll be able to reproduce everything that we're doing. It's all going to be open source and it's all going to be live. You can reproduce all the steps, which we'll share, and you can see how you can start a network testbed on top of the National Research Platform. And part of that is something I'm just going to mention today is that we use our in-house built Sense operator in Kubernetes. So with the use of the Sense operator, users from their end every single user on the cluster is federated through CI logon. By using the operator, users can define their own paths. And you can see here, I don't know if you can see my mouse pointer, but we defined an object, we call it sense path, where users can provide two endpoints, which are basically two nodes on the cluster and interfaces. So node dash 2 dash 6 here would be an actual physical host, a physical server called node dash 2 dash 6 at the San Diego Supercomputer Center. The other one is node-2-7. By specifying a simple YAML as this, users are able to start a path between the interface on this one, the interface on this one, with a bandwidth of, for the sake of example here, 1 gigabit per second. That is guaranteed quality of service bandwidth, courtesy of the ESNet Sense Orchestrator. And users have the ability to either specify an explicit VLAN tag. Of course, that if that VLAN tag is used, that increases the chance of the path not being able to be provisioned and returning an error and explaining to the user that the tag is used. Otherwise, users can drop this field entirely, and this will assign a VLAN tag that is available. And of course, users can also start paths where the other URI, so the other endpoint, doesn't have to be an NRP node just because you're specifying a sense path. It could be another endpoint. And one popular use case here is the a Fabric site where you can have NRP Kubernetes pods that are part of the experiment, and you can have Fabric testbed sites and slices that are running experiments, and you'll have your interface here, your interface here. From the user side, you won't have to deal with VLAN interfaces. They will show as native interfaces, and then you'll be able to conduct your experiments. And the other way to provision is within the pod definitions themselves. So this way, if you set this annotation over here of the target node and this annotation of the bandwidth, this will automatically start the sense path for you and start an interface and attach it to this pod right here. And this is part of what we're hoping to show with hands-on a couple of weeks from now to demonstrate how network experiments work. But very briefly, the sense path starts the path with the orchestrator. So it's a top layer that communicates to the API that Sense provides. And of course, after starting the path, it updates the status by fetching the status from the API. And then the user can either rely on a Multis network attachment definition. A network attachment definition is it's a Kubernetes object that allows us to attach a network interface directly from the host node to the pod that is running Docker containers. Then we patch and update running pods to add the interfaces to them. And this allows us to do multiple interesting experiments. I'm just going to mention a couple of examples about experiments that we've done. by using this infrastructure, this pipeline and workflow that we provide in some of the experiments that we have done before. Like I mentioned, the fabric testbed is one example. As you can see here in this figure, I'm not sure if it shows it in a very clear and intuitive way, but you can see on the right side is that those are fabric sites, and fabric has Alveo U280 FPGAs. They have one FPGA at every site on fabric. And those FPGAs are fully P4 programmable SmartNICs that can use tools like DPDK, can use SmartNIC command line interface tools to interact with these cards, along with them having two 100 gigabit per second ports. So users that provision these resources have full programmability over the device as a network device. And similarly, the National Research Platform, as Elham mentioned, has 32 U55C FPGAs. Those are similar cards in architecture, also with two 100 gigabit per second ports and P4 programmability with DPDK, the exact same workflow that I'm going to be talking about in the next slides, that allows users to provision them as SmartNICs. And here by SmartNICs, we mean fully programmable P4 SmartNICs, where users can define packet processing pipelines and define protocols themselves, define ingress, egress, everything that is happening in the packet processing pipeline, as opposed to relying on readily available tools for standard network protocols. Here, experimenters, especially from multiple science domains, have full autonomy in defining protocols and how they're processed for every single packet that goes through the network and the edge device here, not just the header, but the entire packet itself. And this, of course, relies on the ASNet SmartNIC tool, which is a set of tools, a set of wrappers, a set of prepackaged SmartNIC tools and command line interface tools that are provided by ASNet that allows to use the Xilinx Alveo family of FPGAs, now AMD, so AMD Alveo family of FPGAs. In our cases, the U280 and U55C, to do all the functionalities that I've described and to provide a pipeline where users have a development environment as well. So you can write your own P4, compile it for the FPGAs, and use the compiled P4 artifacts to load the logic on the FPGAs and use all sorts of command line tools, probe counters, and advanced tools like DPDK for more granular control. And that is something that we're also going to be discussing in our talk that is in 3 weeks from now, in an experiment that involves FPGAs and SmartNICs and how to interact with them over the National Research Platform and over Fabric, which both provide a very easy way to use, a very intuitive way to use for these FPGAs to the point where it's a very similar ecosystem for both environments. And that's what paves the way for experiments that involve both ecosystems. And that's one example that we've done. And our main motive here in our experiment in running FPGA telemetry with the segment routing and SRv6 encapsulation, our main motive here in the experiment is reproducibility, is providing the research community with an example where you have a proof of concept. Here it is, it's running, you can see it, it's doing the workload, and then you can take the source code, you can extend from here, you can take the reproducible example and elaborate on it and extended. And basically, to give you a brief idea of what we've done here is that segment routing is the idea, and there have been very interesting talks about segment routing previously with the lunch and learning talks from folks at ESNet. So segment routing is a technique that uses the segment IDs that are predefined in the packet headers by the control plane that steer the packets through the network with explicit segments, so explicit routes that the packets traverse, regardless of routing tables. And SRv6 is the way to do so over IPv6. So there's a segment routing header that is used in the IPv6 definition, and that's what you leverage here. In our example of the full programmability, where you have sort of space for arbitrary packets, what we've done is we've constructed a topology over NRP and Fabric where each segment ID is usually 128 bits for each for its ID. So ID in this example would be an IPv6 address. What we've done is if we've encoded every segment ID into 64 bits and used the other 64 bits for an FPGA timestamp. And FPGA is one of their main use cases here is that they allow for nanosecond level timestamping and high precision telemetry. So what we've done is at every second, every segment that the packet traverses, we collected the timestamps from all the FPGAs on the path. Of course, the path here is between the National Research Platform and Fabric. And we've preserved all the timestamps in the packet headers and sent them towards an endpoint that sends them into towards a database, stripping the payload data, keeping only the headers at every point. And this is a sort of oversimplified way that we constructed our topology. So you can see here in the blue here, these are NRP nodes at the San Diego Supercomputer Center. Each one of these is using one FPGA. And what we've done is we've sent the packets from node -2-7 to node -2-11 through the Fabric UCSD site to their Starlight site in Chicago, Salt Lake City in Utah, then Washington, and then the Fabric Traveling Sienna rack that was on a conference showroom floor, which acts as a collector for all the timestamps that we've had. And you can see here the packet definition of what we were trying to do is that you have your original packet where stripping the payload, taking the headers and putting the headers encapsulated within an SRv6 plus timestamps packet. You can see here, this is your normal SRv6 definition where 128 bits is used for each segment ID. And we've trimmed it to the half because our topology is small, so you can virtually encode your each unique segment into 64 bits and even smaller than that. And you can use the 64-bit timestamp at every site. So this is just to demonstrate one example of P4 experiments, where P4 is the logic of what we're doing with every single packet. That's where we specify how packets are parsed, both in Ethernet, IP, and so on, IPv6 definition, and so on, and where we encapsulate packets and insert timestamps, insert other metadata, also it could be possible, and control ingress and egress, both through P4 logic and through the control plane that is accessed through very easy to use command line tools. And like I said, the Fabric Sienna are traveling rack. So this is a server rack that is on wheels that travels across conferences in North America and sits on the showroom floors for the sake of demonstration. And here in our example, this was to demonstrate the capabilities of those cards and ecosystems that NRP and Fabric have to offer. A very simple, very similar experiment that we've done is that we've taken the same experiment, but this was a simpler experiment where we just demonstrated microSID SRv6, where the segment IDs are all encoded into one segment ID, into one 128-bit field. With this offers for a more compact, smaller size and headers for packets that allows for higher throughput and higher packet processing rates. And of course, this was also an experiment that was combined between NRP and Fabric. And like I said, the main motive here is reproducibility, is giving something to the research community that can be, let me call it an artifact that users can take and build on top of. And this is one thing that we provide in our documentations, as Elham has mentioned, so docs.nrp.ai. This is where we have all of our docs, and joint experiments with Fabric is one example that we show that it's an experiment that goes from A to Z in starting an, let me call it interoperability proof experiment where there's two ecosystems. You can see that we also have our FPGA SmartNIC documentations on how to use the FPGA tools and get up and started with them. And now I'm just gonna steer into something slightly different, but somewhat relevant in the same area, is measuring and monitoring over the National Research Platform. And one thing that the National Research Platform and folks at Inmon have provided for the National Research Platform is full observability and controllability with SFlow. So every node on the National Research Platform has SFlow and the SFlow daemon running on it. So SFlow and HSFlowD. And that allows us to packet sample and look at the network in full observability on the National Research Platform and see drop events, see what's happening on the network in real time. And this is, of course, done by having, like I said, the daemon on every single node, monitoring the interfaces, monitoring drop packets, both in the kernel stack and as well as communicating with the network switches that provide connectivity for the National Research Platform, and monitoring TCP flows and collecting metrics, both in delay and jitter and so on. And as well as peeking into other metrics as well, such as GPU related metrics and container metrics as well. And of course, there's the SFlow RT analytics engine that processes all the SFlow data, and it's all demonstrated in Mon dashboards. So you can see here, and these are, of course, our screenshots courtesy of Inmon from running their stack of tools on the National Research Platform. You can see here we have all of our nodes here, and of course, the more you have, the more you can plug in. No bottlenecks anywhere, and you can look at all network packets between any two endpoints, for example, any one node, any one interface. At every single level, you can see packets dropped, ingress packets, ingress flows, outgress flows, drop rates, latencies, jitters, and so on. So that is one level of how we provide observability inside the National Research Platform. The other way is that we have Prometheus metrics and Prometheus collectors for every single metric that we can think of. So we're scraping the metrics from every single node that is on the cluster, every single hardware resource that we can pull metrics from, whether it's storage, whether it's GPUs, CPUs, memories, FPGAs, SmartNICs. Our LLM use is also monitored in Prometheus, and our different file systems are monitored in Prometheus. And all those Prometheus exporters, they're all integrated into Grafana dashboards. So we have more than 50 dashboards, and these are all publicly available where anybody interested can take a look at the data behind the National Research Platform and the things that we run. And Prometheus itself is public as well. And we've provided the links here. So prometheus.nrp-nautilus.io is where all the Prometheus AI has access to all the Prometheus data, and grafana.nrp-nautilus.io is where we keep all of our publicly available Grafana dashboards, and where users can access them. This is very interesting for namespaces as well, and users within their namespaces where they can monitor their own resources, get a little bit of observability towards what's going on with their workloads on all levels. So the storage classes they're provisioning, their individual pods and individual containers, and their resource use across metrics. And for long-term storage, we also use Thanos with S3 backed storage. As Elham mentioned, we provision S3 for cluster users, and we have our S3 storage backing Thanos for a long time. I believe it's 5 years of metrics on Thanos. And we're gonna end a little bit early here. Thank you all for listening to our talk. As we mentioned, our main website link is nrp.ai. By visiting that, you can see the services we provide, the partners we collaborate with, and then sort of scientific workflows, HPC workflows, AI workflows, and all the research work that is being done on the National Research Platform, as well as classroom and courses and education use cases. And on rp.ai/contact is where you can see the links for our Matrix server. As Alham mentioned, that's where the community lives. That's where you get to interact with everybody, and that's where you get the almost real-time user support from all of our operator team and our operations team. And you get access to how to get access to the cluster, step-by-step guides, and you can see resource utilization, all of that. It's all on nrp.ai. And we're just gonna end a little bit early and see if anybody has any questions here. Would be more than happy to answer them.
All right, thank you both for going through all of that. So I've given everybody the ability to unmute yourself. If you do have questions and want to ask them, you can type them in the chat, or you could raise your hand and we can acknowledge you and you can ask them directly. while we're waiting for people to ask a couple of questions, I don't know if you said it in there, but how could people go about joining NRP to donate resources, not just be users of it?
Yeah, so we've made that model very simple with what we call our Bring Our Own Resources initiative. So in terms of the technical details of how hardware is joined into the National Research Platform, it's a very easy model where all you have to do is provide the hardware behind a Science DMZ or behind a network that doesn't have any strict firewalls. And ideally, if it has IPMI access, that's all our admins would need to do. So from our IPMI access, we can go into the nodes, whatever environment they have. See, John sent the link in chat on our doc page on how to join NRP. And once we have IPMI access, we go in the node. We have Ansible playbooks that we've configured to do everything, and we install everything, run everything, and join the hardware to the cluster. And it's important to say that we have a very wide variety of hardware. So whatever the hardware resources are, I believe we still have Raspberry Pis that are part of the cluster as well that's showing as devices. So we try to deal with as big of a variety of hardware as we can. But in terms of network requirements, as long as it's behind a Science DMZ, like I said, and we have SSH IPMI access, we're able to configure it from our side. And then they can provision their own hardware. And we have instances where folks at institutes would like to join hardware but get priority access to it. One example is if a node is being used for, let's say it's being used for classrooms, but in its downtime, they want to sort of federate it for everybody else on the cluster. That is also a model that we support and we can provide support to.
Okay, thank you. Does anybody else have any questions that they'd like to ask? Kurt is asking in chat, can you say a little bit about East and West regions and why users would choose one or the other?
Yeah, so the main way to look at it is that we've organized the cluster into regions. So we have the West region where uh, the West Coast is, and the Central region mainly UNL and partners are on the map. So the central region of the United States, and we have East, so East Coast, uh, or let me say called Northeast. And so East is East Coast, but we have Southeast, which is the area around Florida, basically. So the Southeast Coast. And we provision storage pools. So those are nodes that are provisioning storage to everybody on the cluster. And of course, all four regions that I mentioned are publicly available to everybody, but users can set that they want to start their pods in a region as opposed to another to be closer to their data. That is in terms of in general, regions in general. But Kurt, if your question is mainly about JupyterHub, it's because this is a scalability approach where we have two separate JupyterHub environments just to load balance between the two because the folks that developed the JupyterHub Helm approach are working on scalability and having it not let me say lag in very big instances, but we mainly use Jupyter Hub West as our main one, and we have Jupyter Hub East just to have a, let me call it a safety net that we have another instance that users can use as well. So in terms of Jupyter Hub, the TLDR is that both are available, both are easy, both are up to date with the same images, same features, but we recommend West more because a bulk of our resources is on the West Coast. So more often than not, if you use the West one, you're more likely to be closer to the resources you're requesting, both in terms of storage and the compute resources.
All right, thank you.
Thank you.
Does anybody else have any questions for today? All right. Well, thank you both for going through the initial stages of this. As a reminder for everybody, we're off next week for the holiday, and then we will have the second talk on July 11th and the third talk on July 18th. And I'll make sure I get this video posted. And if Mohammed or Elham, if you want to just shoot me a link to the slides, I'll make sure that those get posted too.
That sounds
Thank,
perfect.
thank you, everybody. Hope you have a good weekend.
Thank you all.
Thanks all.